moving on to applications of Gauss theorem. And before that, let's introduce a new term, Gaussian surface. What do we know about it? We will always consider Gaussian surface when we prove any application from Gauss theorem. These surfaces are used to find electric field for any arbitrary point or group of charges or any single charge. So Gaussian surface can be defined as these are imaginary surface equipotential in nature about a charge or about a group of charges from which the electric field is to be found out or to be deduced. Second point, while you do the application of this Gauss theorem, remember two simple steps. First, you find the value of flux. What was flux? E dot ds. That is surface integral of electric field about a closed surface. First, find its value on your own. Do not equate it yet. Second part, once you have got your value, equate it with the value of q upon epsilon naught, which was according to Gauss theorem. In doing so, you will get the value of electric field of whatever surface or charge or group of charges you are looking for. Let's start it out. How many charge distributions do we know about? Linear charge distribution, surface charge distribution, and volumetric charge distribution. We will come back to that point, but first we will do, let's to deduce Coulomb's law from Gauss theorem. Okay, let's do this point first. Consider a charge q. This would be my introductory line. Consider a charge q having Gaussian surface spherical of radius r. What is the first step I would do to find or to use this application? First, I'll find the value of E dot ds, that is the value of flux. And to calculate the value of flux, I'll be starting with, consider a charge q having Gaussian surface spherical in nature of radius r. Let total flux from the charge is given by E dot ds. Now what is ds? Where is this ds? I will consider a small surface patch, a small area element on the spherical surface, and I have to find its the area vector. What is area vector for? I have already discussed about it, but let's go back. What is area vector for a spherical surface? Area vector for this plain whiteboard will be a perpendicular vector. Area vector for a flat surface would be this, perpendicular. Area vector is always perpendicular to the area. So on spherical surface, a sphere is a round like a ball. What will be the area vector of any patch on the wall? It is the radius extended, the normal, which you will again do in the optical chapter. This normal, this radius, if you extend it, it behaves like the perpendicular, because this radius is actually perpendicular to the tangent. This is the logic behind it. So this was the area vector. Now flux, which is equal to E dot ds, I have considered a small area element. The area vector would be vertically outwards, and electric field, since this is a positive charge, electric field lines are radially outwards from every point. So both of these are in same direction. Considering this fact, first you will remove the dot product. E dot ds is E ds cos of theta, which will be cos of 0 degree. I am writing it here only. E dot ds, that is E ds cos 0. Cos 0 is 1, so you are left with E ds. I am taking E common out. E is a constant, it will be out. Why E is a constant? Because at a constant distance, E will be same for all values of r with this charge. So E is a constant, integration ds. What will be the integration of ds? ds will give me the complete surface area of the sphere of radius r. So the answer is E into 4 pi r square. Alright, this is the value of flux which I have deduced. Don't put the value of E in this equation. Why? We are deriving the Coulomb's law from Gauss theorem, we are deducing it. I know we already know the value of E, but we are not going to put it here. We want to find the value of E using Gauss theorem. So This is our equation 1, but the second part which I just told you how to use applications, first find E dot ds on your own, and second put it equal to q upon epsilon naught. So according to Gauss theorem, don't write GT, please write whole complete Gauss theorem. According to Gauss theorem, flux is equal to q upon epsilon naught. This is our equation 2. From equation 1 and equation 2, both these equations are for the flux. So what will you get? E into 4 pi r square is equal to q upon epsilon naught. That means E is equal to, all this term goes down. So q upon 4 pi r square into epsilon naught, or I can rearrange these figures, 4 pi epsilon naught into r square. So basically now we have got the same formula of electric field which we already knew. So E is equal to q upon 4 pi epsilon naught r square, but our motive was to find or to prove Coulomb's law. Then you would be start writing another statement here. Consider a charge q naught placed on the surface. So the force experienced by q naught will be q naught E. This was from the definition of electric field, and instead of E, write this value, consider the point, this value is derived from using the Gauss theorem. So q naught into q upon 4 pi epsilon naught r square. What exactly have we got here? This is 1 upon 4 pi epsilon naught q naught upon r square, basically q1 q2 upon r square, and this proves the Coulomb's law.